Okay, continuing with a couple of examples, let's try to integrate the absolute value of the sine of x dx. Now, whenever we have to differentiate or anti-differentiate absolute values, the very first thing you want to do is get rid of those absolute value bars. And so if we take a look at the sine function, we can kind of see what's happening. The sine function starts at 0 and starts oscillating. That's 2 pi. That's pi. So that's pi over 2 and 3 pi over 2. So the sine function is very symmetric. And so we want to find the area between the area of that region right there. So the absolute value of the sine would actually flip this up, right? Well, maybe I'll use a different color. So this would be the absolute value. Okay, and so actually if you look at the graph, right, if you knew this area right here, then you could just make it 3 times that, and that would be your answer. So let's go ahead and do that. So that's how I would integrate this. I would take 3 times the integral from 0 to pi over 2 sine of x dx. Now the reason we can do that, right, is that we have that picture that we could go off of, because otherwise we wouldn't know, where to start. Okay, so that would be 3 times, let's see, the antiderivative of sine is cosine. Minus cosine. And from 0 to pi over 2. So it's minus 3. Minus 3 cosine pi over 2 plus 3 cosine of 0. Good, cosine of pi over 2 is equal to 0. Cosine of 0 is equal to 1, so therefore overall we have 3. So actually you can see each of these little wedges right here has an area of 1. That's kind of nice. Good, all right. Okay, so our last topic that we want to cover is something from 5.5, and that is integration by substitution. And the reason we want to get this in is because at this point of time, right now, if we were to stop here, we would only really know how to anti-differentiate just really, really basic functions. And so it's good to know how to anti-differentiate a little bit more complicated functions, although that's really the topic of Calc 2, is to really design different methods for solving antiderivatives. So in order to start this, maybe we should think about what the chain rule is, and then we'll try to go take a backwards rule. So the chain rule says that the derivative of f of g of x is equal to f prime of g of x times g prime of x. Right? So therefore, if I integrate both sides, then I get the f of g of x is equal to the integral of f prime of g of x times g prime of x dx. Now this would be hard to recognize that you actually have this form. So the way we do this is we usually make some kind of a substitution. If we see a composition like this, substitution, we let u be equal to g of x. So, and then we need our differentials for the integral, so that du is equal to g prime of x dx. And then if I make these substitutions into my integral, well, let me rewrite the integral down here. Oops. So the integral of f prime of g of x, g prime of x dx, becomes the integral of f prime of u du. And now this is really easy to anti-differentiate, right? That's just f of u, which of course is f of g of x. Good. And so this is actually how you want to work these. So if you're given an integral of something and it looks like a composition, try letting u be equal to your inside function and then figure out what your differential is. Good, so let's give that a try. So here's an integral 2x plus 3 divided by the square root x squared plus 3x plus 1. Wow, this looks really complicated. However, I'm thinking that the thing inside the radical is probably the inside function. So what happens if I let u be equal to x squared plus 3x plus 1? Can I find my differentials for my substitution? Right, so du over dx, or just du, is going to be 2x plus 3 dx. And of course you'll notice what's sitting in your integral. Yes, 2x plus 3 dx. So now we can make those substitutions. In the numerator here, we can substitute this for, this is du, right? And then in the denominator, we just have u to the 1/2 power. So rewriting that, that would be u to the minus 1/2 power du. And now we can integrate that pretty easily, right? That's just u to the 1/2 times 2. You can add c if you like. Well, we should add c. It's not whether you like it or not. Okay, so now that's just the one thing to remember is to back substitute at the very end. So we just have 2 times the square root of x squared plus 3x plus 1 plus c. Good. So there is our answer. So notice that I had to guess that what the inside function is. Sometimes it takes a couple of guesses to figure it out, but hopefully not too much more than that. Let's try another one. How about the integral from 0 to 4 now of the square root of 2x plus 1 dx. Good. Now, this one is probably looking like that's going to be your u, right? So if we let u be equal to 2x plus 1, then du is equal to 2 times dx. And so notice I don't have a 2 in my integral, and so I could solve this for dx, right? I could write that dx is equal to 1/2 du. Okay. Also, I've got these numbers 0 and 4. Those are in terms of x. I would like my integral to be in terms of u instead. So if x equals 0, what is u? U is equal to 2 times 0 plus 1, which is 1. And then if x is equal to 4, then u is equal to 2 times 4 plus 1, which is 9. Okay? And so now we can make our substitution. So that's going to be the integral from 1 to 9 of u to the 1/2 power du. Good. And so now, what's nice about this is you don't have to revert back to x now. So when we solve this, that's u to the 3/2 times 2/3 from 1 to 9, right? That's just going to be 2/3 times 9 to the 3/2 minus 1 to the 3/2. Right, so now we don't have to convert back to x at all. What is 9 to the 3/2? That's the square root of 9 cubed. So that's 27. Oop, I was just looking over my answer and I think I missed something. Did you guys catch that? Did you yell at me? Boy, I'm making all kinds of boo-boos here. Yeah, my dx is 1/2 du. So that's 1/2 is still there. The 1/2 cancels. I'm just left with 1/3. Good. I should have cut that earlier. So this again is the square root of 9 cubed. So that's 27 minus 1. Or 26/3. Good. All right, let's try another one. I'll pause here while I write it down. All right, so for this one, let's play a little game. Let's try to guess the substitution that we would use. So for number 1, what would you guess? What substitution would you use? Go ahead and pause. Are you back? Did you guess u equals x cubed plus 5? So then du would be 3x squared dx, or you could write 1/3 du is x squared dx, because I'm seeing over here, right, that x squared dx. Good. All right. And how about the next one? Can you guess the substitution for number 2? Go ahead and pause. Are you back? Did you guess u equals t squared plus 1? That's the one I would guess. So then du would be 2t dt. Or again, you could divide by 2, so 1/2 du would be your t dt, which is sitting right here. Let's use a different color. Good. All right. How about number 3? Are you back? So this one might be a little bit trickier. I think we would want to use u as the inverse tangent of t. Why is that? Because did the denominator here look familiar? It is the derivative. Yeah. So if you make the substitution, right, you're just left with the integral of u du. Good. All right. That was kind of a tricky one. How about the sine of x over 1 plus cosine squared? What might you make a substitution with? Did you say cosine? I think I may make it with the cosine. Because let's see why. If u is equal to the cosine of x, then du would be minus sine of x dx. And so I could write minus du then as plus sine of dx dx. Sine of x dx. So that would take care, the substitution, right, would take care of the, oops, sorry about that, the sine of x dx, and then I would be left with the integral of 1 over 1 plus u squared du. Do you remember what that is? Sitting right here. That is the inverse tangent of u. Okay, I went too far on that one. How about the next one? Maybe I can trick you on that one. All right, you can let u be equal to, you can let u be either x squared or minus x squared. Doesn't matter. If you let u be equal to x squared, then du would be 2x dx, or you could take the 1/2 and take out the, so then you have your x dx, right, that you're seeing here. And so you would also want to be sure and make substitutions for 0 and 1 when you're doing that. Very good. Okay, we kind of ran out of time there. We might do one more video. It's this is our 3rd video for this set, but maybe just another video of examples.